Just a quick reminder before we get into the lesson to download the hands-on lab exercises that accompany this complete CCNA course. I'll include the link in the description. Also remember to subscribe and hit the notifications bell so you don't miss any of the lessons in the course. Okay, let's get into it. In this lecture, you'll learn about how spanning tree works. This is going to be a bit of a longer lecture because there is a fair bit to spanning tree and there's not really any logical points where I can break this into separate videos. So this is a good time to go and grab yourself a coffee and then come back and settle into the video. Okay, so how spanning tree works. It's an industry standard protocol which is enabled by default on all vendors' switches. You've already seen how devastating a broadcast storm can be on a local area network. We need to avoid that at all costs, and spanning tree is how we do it, so it's always enabled on all vendor switches when they come out of the box. Switches send BPDUs, Bridge Protocol Data Units, when they come online. And the BPDUs are used to detect other switches and potential loops. The switch will not forward traffic out any port until it's certain that that port is loop-free. When the port first comes online, it will be in a blocking state because the switch needs to make sure it doesn't send traffic until it's sure there's not a loop there. Spanning tree will detect if the port forms a potential loop, and if there's no loop, the port will then transition to a forwarding state. But that process can take up to 50 seconds if you're using traditional legacy spanning tree. The BPDU contains the switch's bridge ID, which uniquely identifies the switch on the LAN. And the bridge ID is comprised of the switch's unique MAC address and also an administrator-defined bridge priority value. The bridge priority can be from 0 to 65535, and 32768 is the default. So switches, they're always going to have a MAC address on them. That's there out of the box. The bridge priority can be set by you, the administrator. But if you don't set that, it's going to default to 32768. Next thing we have is the root bridge. A root bridge, a single root bridge, is elected based on the switch's bridge ID values. The switch with the lowest bridge priority value in the LAN is preferred to be the root bridge. So if the bridge priority value is 16384, for example, that would be more preferred than 49152 because it's a lower number. In the case of a tie, the switch with the lowest MAC address will be selected. So going back a slide, if you don't manually manipulate this by manually setting a bridge ID, all the switches in your LAN will have the same bridge priority, which will be 32768. In that case, they'll all have a tie, so it will be the one with the lowest MAC address that will be selected as the root bridge. The switches build a loop-free forwarding path tree which leads back to the root bridge. And you'll see how this works as we go through this lecture. So a spanning tree example. In our example here, we've not manually set bridge priority on any of our switches. We've got 4 switches here, CD1, the CD is for core distribution, CD2, and we've got access layer 3 and access 4. CD1 has got MAC address 1.1.1. It's actually 1111.1111.1111, but to make it a bit shorthand, I've said it's MAC 1.1.1. CD2 is MAC 2.2.2, Axis 3 is MAC 3.3.3, and Axis 4 is MAC 4.4.4. Because I haven't set a bridge priority on any of the switches, CD1 will be elected as the root bridge because it has got the numerically lowest MAC address. The other switches will then detect their lowest cost path to get to the root bridge, and those paths will transition to a forwarding state. For the cost, when a switch calculates its best path towards the root bridge, higher bandwidth links are preferred. So a gigabit Ethernet interface would be preferred over a lower bandwidth fast Ethernet interface, for example. Each switch's exit interface on the lowest cost path towards the root bridge is selected as its root port. So if you have a look at the diagram here, we already said that CD1 is the root bridge. From CD2's point of view, it's got two paths. Actually, it's got three paths it can take to get to CD1. It can go out interface gigabit 0/2, it's directly connected to CD1. Or it could go via access 4 by going out fast 0/24 and then out fast 0/21 on access 4. Or it could go via access 3, so it would go out port fast 0/21 on CD2 and then out port fast 0/24 on access 3. Hopefully it's really obvious which is going to be the lowest cost path out of those three. It's going to be the direct connection along the top on the gigabit 0/2 interface. So on CD2, interface gig 0/2 will be selected as its root port. Next up, we have access 3. Access 3 could get to the root bridge CD1 either out interface fast 0/24 directly, or it could go out interface fast 0/21 to CD2 and then across on interface gig 0/2. Again, it should be obvious that a single fast Ethernet link is going to be a lower cost than a gigabit Ethernet plus a fast Ethernet link. So access 3 will select port fast 0/24 as its lowest cost to get to CD1, and that interface becomes its root port. And then finally, we have access 4, and it should be obvious again which will be the root port on access 4. It's going to be interface fast 0/21, which again is directly connected to the root bridge of CD1. While I'm going through this, by the way, this is how the spanning tree operations work as well. The first thing that happens is a root bridge is elected. So all the switches come online, they send BBTUs to each other over the LAN, they all detect each other, and whichever bridge has got the best bridge ID, so the lowest priority, if there's a tie, it'll be the lowest MAC address, becomes the root bridge. That's the first thing that happens. The next thing that happens is that all the switches in the LAN will figure out which is their root port, the best port to get towards the root bridge. And we'll carry on going through the operations through the rest of this lecture. Now, importantly, spanning tree does not do load balancing. If a switch has multiple equal cost paths towards the root bridge, it will select the neighbor switch with the lowest bridge ID, and that is going to be just one path. So you see in the example diagram here, core 1 is the root bridge now. And looking at it from axis 3 down at the bottom's point of view, it's got two equal cost paths it could take to get to the root bridge core 1. It could either go out interface fast 0/24 on the left hand side, or interface fast 0/23 on the right hand side. Now, spanning tree, it's not a dynamic routing protocol. If this was a routing protocol, it would do equal cost load balancing and traffic would go up both paths. But with spanning tree, it doesn't do load balancing, it selects the one best path. So what happens here is axis 3 selects the path to the core 1 root bridge via distribution 2 as it has a lower bridge ID. Whenever there's a tie, the switch will select the neighbor switch with the lowest bridge ID, and that is distribution 2 in this case because it's got a lower MAC address than distribution 1 does, and we didn't set priority on either of them for this example. Another example of load balancing. So if I go back a slide here, we had two equal cost paths towards the root bridge going through two different switches. In this next example, again, spanning tree does not do load balancing. If a switch has multiple equal cost paths via the same neighbor switch towards the root bridge, again, it will only select one of those paths. It will select the port with the lowest port ID. So the example here, we've actually got 4 uplinks towards the root bridge core 1 from access 3. We've got 2 going towards distribution 1 and 2 going towards distribution 2. Out of those 4 uplinks, only one of them is going to be selected. Access 3 will select the path to the core 1 root bridge via distribution 2 port fast 0/1, as it is the port with the lowest port ID, which is going to the switch with the lowest bridge ID. Okay, moving on. So first thing, we select which is the root bridge. Next up, all of the other switches select their root port towards the root bridge. Next thing is designated ports. Ports on the neighbor switch opposite the root port are designated ports. So your root ports point towards the root bridge, designated ports point away from it. And all ports in the root bridge will always be designated ports, because obviously they are going to be pointing away from the root bridge when they're on it. So in the example here, we already discovered which were our root ports. On the interface on the other side of those links, they will be set as designated ports. So looking at CD2, its root port was gig 0/2 along the top. The interface on the other side, which is gig 0/2 on CD1, will be set as a designated port. The next one is facing access 3. Access 3's root port was fast 0/24. The interface on the other side of that link is fast 0/24 on CD1. And finally, it should be obvious that access 4, its root port is fast 0/21. So the designated port will be on the other side of that link. It's going to be on fast 0/21 on CD1. And you can see here that all the ports in the root bridge are always designated ports. Now, looking at that previous example, you're maybe thinking, well, it's obvious which are the designated ports, it's just all the ports that are on the root bridge. But that's not necessarily the case, because you see here, I'm going to add another switch into the network, which is not directly connected to the root bridge. It's connected to CD2. If you look at that switch, it should be pretty obvious that its root port is going to be on the interface facing CD2, and then the designated port will be the port on CD2, which is facing back towards that root port. So whenever we've got a root port, the interface on the other side of the link is going to be a designated port. Your root ports and your designated ports are the most direct paths to and from the root bridge. And the root bridge serves as a central point of the networking for where our traffic flows are going to go to and from. So because your root ports and designated ports are on the most direct path, they are always going to transition to a forwarding state. On the remaining links, the switches determine which of them has the least cost path to the root. If they have equal cost paths, then the bridge ID is used as a tiebreaker, and the port connecting this switch to the link is selected as a designated port. So looking at our diagram again here, you see that we've got 2 links left over which have not been configured with root and designated ports. That's the link from interface fast 0/21 on access 3 to fast 0/21 on CD2, and the other link is on access 4 port fast 0/24 going up to fast 0/24 on CD2. On those 2 remaining links, they're links that would form a loop, so we're going to need to block. And we're going to block on one side of the link, the other side of the link will remain a designated port. So right now we need to figure out which side will be the blocking side, which will be the designated port side. The side which has got the switch with the least cost path to the root, or the lowest bridge ID, will be the designated port side. The other side will be the blocking port. So right now, CD2 has got a gigabit Ethernet direct link going to the root bridge of CD2. That's going to be lower cost than Access 3 and Access 4, which have got fast Ethernet links. So CD2 is going to be the preferred switch, so it's going to have designated ports on each side of those links. So from Access 3 fast 0/21 to CD2 fast 0/21, the CD2 side is going to be the designated port. And it's also going to be the CD2 side, which is the designated port, going on the link on fast 0/24 down to Access 4. Any ports which have not been selected as a root port or a designated port pair would potentially form a loop, and those are going to be selected as our blocking ports. So you can see on the diagram right now, we've only got 2 ports left over. That's fast 0/21 on Access 3 and fast 0/24 on Access 4. If those ports were also forwarding, we would be forwarding everywhere and we would have a loop. So we're going to block on those ports to break the loops. So we block on fast 0/24 on Access 4 and on fast 0/21 on Access 3. And you can now see that I've completed my diagram. Every single port has been labeled as either a root port, a designated port, or a blocking port. Spanning tree only blocks ports on one side of the blocked link. BBTUs continue to be sent over the link, but other traffic is dropped. So we continue to send BBTUs so that spanning tree can detect if any links go down and fail around to a different path around that. Okay, so we covered how to figure out the root, the designated, and the blocking ports. I'll summarize here about the quick and easy way to do that, which really aligns with how spanning tree actually works as well. So first off, determine which is the root bridge out of all the switches. That will be the switch which has got the best bridge ID. Next, all ports on the root bridge are designated ports. So if you've drawn this as a diagram, on your diagram, on all the ports that are on the root bridge, you can mark them as DP, designated ports. Next, determine the root ports on the other switches, the non-root bridges. The root port will be the port which has got the lowest cost to the root bridge. Mark those as RP, root ports, on your diagram. Next up, the ports on the other side of those links, on the other side of your root ports, are going to be designated ports, so you can mark them off. And then on the links which are left over, one port will be blocking, the other side will be a designated port. Determine which is the blocking port. That's the one which has got the highest cost path to the root bridge or the highest bridge ID. The ports on the other side of those links are designated ports. You've now completed your diagram. You know all the ports in the network, what type they are. So going back to our original diagram, showing the entire network here, and if you look back at the previous slides with the diagrams, this was just a zoomed in, drill down level of the switches. So going back, this diagram here, I've zoomed back out again to show the entire network. So those are the available paths through the network. If you look at the switching part here, you can see I've removed the links which were blocked. All unicast, multicast, and broadcast traffic, so all the traffic on the network, can only go over those links. If you look up at the top part of the network, you see that there are loops between our routers, but routing protocol loop prevention mechanisms and the TTL field in our IP header prevent traffic from actually looping at layer 3. Looking at the switched part of the network, you see that there are no actual loops there now. They've all been removed by spanning tree. So spanning tree ensures that there are no loops at layer 2. And if we go back to the ARP request that we covered at the start of this section, where PC1 sent out an ARP request for its default gateway at R1, you can see that now we are using spanning tree, the traffic still gets flooded everywhere over the tree, but it doesn't get looped anywhere. So traffic can still get where it needs to go, but we're not going to have any broadcast storms formed by loops. If an uplink to CD1 fails, spanning tree will detect it and transition the redundant link to forwarding. So you can see in the example here that my uplink from access 3 to CD1 and my uplink from access 4 to the root bridge at CD1, both of those failed. If that happens, then spanning tree will detect it and it will fail it over to the next best path, still ensuring that there are no loops. So this is what our topology would look like if we had lost those uplinks to CD1. You can now see that we still have just that one spanning tree again with no loops in it. Now the traffic is going via CD2. Okay, we got there. That's it. You now know the whole thing about how spanning tree works. In the next few lectures, we'll get into how to actually monitor and configure it. Thanks for watching. If you'd like to get the complete course ad-free right now, then you can enroll in my CCNA Gold Bootcamp by clicking the link above my head or in the description. It also includes full study notes, quizzes, and 150 pages of additional troubleshooting labs you can't find anywhere else.